Hello everyone, welcome. So today we will be going through this companion notebook that we have prepared for week 3, which highlights k-means, k-means plus plus and the related topics covered in the course. So first we construct this toy data set with 3 clusters, and we first investigate why we even require a clustering paradigm. So we see that this clustering is present, but when we run PCA, which is a representation learning algorithm on linear subspaces, when that is applied to this particular data set, we see this information about clustering is kind of lost. So therefore this kind of motivates the requirement for a clustering paradigm in our non-supervised learning paradigm, and so we postulate this k-means clustering Lloyds algorithm. So given some choice of k, we had to find k distinct points that kind of best represent our data set. So for example, here we want to say find 3 points, we want to compress the set of 200 points into just 3 points. That is kind of what we are trying to do here, and we do that by formulating our objective as follows. We want to minimize the sum of distances between the closest center and the data point, and so we have to find which cluster assignment Z does this for us. The strategy we postulate is the Lloyds algorithm. The Lloyds algorithm has 3 broad steps. The first one is an initialization step where we choose in this case 3 random data points from the data set as cluster centers. Then in our cluster assignment step, we assign a new cluster, we assign Zi based on these cluster indicators. For example, if we consider data point xi, we calculate the distance between mu1, mu2 and mu3. We see which distance is smaller, and correspondingly we assign, for example, if the distance is smallest with mu3, the data point xi will have a cluster indicator of 3. So Zi would be equal to 3. Thirdly, we decompute the cluster centers. Since we have assigned different clusters, we can use these clusters, find the mean of only these clusters to obtain a new cluster centers, and then these 2 steps are repeated until convergence is achieved. Now convergence is established because we can say one thing is that our objective function is the sum of squared terms, right? So it wouldn't be wrong to say 0 is a valid lower bound that we have for this particular objective function. And secondly, Lloyds algorithm can be proved to strictly reduce after every iteration, and this is shown using the intermediate step that is discussed in the lectures. We will be going through that in detail shortly. For now, on this particular data set, we perform this thing. So initially we choose some random clusters, that happens to be these 3, and then we assign clusters based on the proximity from the data points. The proximity, right? So these lines correspond. For example, if I take these 2 data points, I connect them and draw a perpendicular bisector. This kind of corresponds to the locus that differentiates which data points are closer to which cluster center. And I can also go ahead to say that for every cluster indicator, there exists an intersection of half spaces that correspond to whatever data point is assigned to that particular cluster, which is also called a Voronoi partition. So by assigning certain cluster centers, I am essentially formulating a new Voronoi partition, and k-means is at the end is trying to find the best Voronoi partition that minimizes our objective function that we have postulated. Now that we have this, we have assigned we have taken a random initialization, we have assigned points. Now we go ahead and recompute the means. If I recompute the means, you can kind of see that this data point would sort of shift here, this as well, but the green not as much, because you can see there are much more yellow points on the left as compared to the green points. This will also go up, so it can be shown as follows. So I have this initial one, then the yellow goes here, the Voronoi partition is accordingly changed, and we converge at the end of our second iteration, which happens to be this. Now this was a simple data set. We will generate a complex data set with 6 clusters and see how it goes with that. So we have this particular data set with 6 clusters, and we run Lloyds algorithm on this, right? Alright, so this is our initialization. So these have been the 6 clusters that have been chosen at random, and the cost you can see is around 2000, and we will run objective on this. So first initially, so when I recompute my clusters, right, you can see I have not colored these points according to the Voronoi partition yet, because this is also dotted. The right hand plot actually denotes the objective function for each iteration. This diagram corresponds to the intermediate step that is discussed, right. So here, without coloring, we just updating the centers give us the following drop in objective, and this is a strict drop, which is why we show this is what is used to show that Lloyds algorithm necessarily converges for any initialization. But the nature of the solution need not be the same. So we will go on to that later as well. So this is the intermediate step, and at the end of iteration 1 we come to this particular assignment. Then we go on to the next step, the other intermediate, and then the end of the second iteration, and if this continues we have the following, right. So you can see it's sort of battling with every other cluster to converge to the final thing, but the final solution seems to be the solution that we also want, right. But k-means with a random initialization especially need not always converge to a good or ideal clustering that we are looking for. For example, consider this following scenario. This has been the cluster initialization, right. So you have 4 points in one particular thing. It's random. Any cluster assignment is equally possible. So therefore we start with this cluster assignment and see how we progress. You can see these two data points here are sort of battling with each other to get this particular cluster, but they sort of converge, right. They are sort of okay with this battle, and there is no pushing of this yellow by this green so that it could occupy this unoccupied cluster, right. So here this data point without any battle is sort of occupying both of these two clusters. So this motivates the fact that k-means the initialization in k-means is paramount, and therefore maybe if you want a good initialization, maybe you run it several times on your data set and see, or we could use a smart initialization process. So you can see the clusters are initialized very close to each other. So that we kind of hypothesize will not really lead to the optimal or the ideal ones that we are looking for, which is the approximation of the NPR problem. So we argue that, say, spreading our data points out equally might help in increasing the probability of it in getting this ideal clustering. So that is our hypothesis. So underlying that, we come up with this new initialization strategy. It's called the k-means ++ algorithm. So here what is different is that, so the first data point you sample at random. So it is from a uniform distribution for all data points. Once you choose a particular data point, you score every other data point based on how far away it is. So you want data points that are far away from your collection of selected clusters to be more probable for you to select, right. So that probability is proportional to the squared distance from the collection of points. So that is how k-means ++ works, and we demonstrate that also in this particular this thing. So yeah, so this is our initial data set. So we run k-means ++ to initialize our clusters on this. The first one is random, so there is nothing new. The second one is probabilistically chosen, so that it is the points that are far away from this particular data point. So points such as these are more likely to be chosen than points such as this or this. So the second point happens to be that, and the initialization goes on like that, and you can see, right, there's something wonderful happening. The fact that all these data points are sort of conveniently initialized to one cluster each. So we run it with this initialization. There is nothing abundant that will happen by Lloyds. You just sort of refine your cluster indicators to make sure they are the midpoint of all these particular clusters. One other note is that the choice of k, right. So here we have gone with this notion that k is equal to 6 because conveniently we have generated this data set here, but that might not necessarily be the case in practice. So how will you go about choosing a choice of k? So for that, this is called the elbow method. So you have a set of k's, and then you run k-means or k-means ++ whatever. For every choice of k, you kind of try to approximate the NPR solution and get the least value that you get from the experiment. So that will be your plot for one particular choice of k, and you do this for all your choices of k, right. And then you see after which point is your increasing of k not substantially affecting the objective value, and you choose that to be the optimal value for k. Or you could incur a penalty for every choice of k. So this is a linear penalty that I have here. There could be many other penalties. So if you could incorporate that, then it's a simple optimization problem. You see which value is just the minimum, and you choose that to be your value of k. In this, as we expect, we get the value of 6 to be the optimal choice of k for this particular data set, right. Finally, we compare these two strategies. the random strategy versus the initialization strategy, the random versus k-means plus plus. So we run 1000 trials on the same data set that we have constructed, and these happen to be the results. The objective value for our ideal assignment happens to be around 174, and out of the 1000 trials, around 480 trials have converged to this particular assignment, whereas in k-means plus plus it is around 800 something. An important thing to note, right? So k-means plus plus need not necessarily always converge to the optimal solution that we are looking for. So here in this case, even with k is equal to 6, it converges to that particular assignment only 80% of the time. So that is something to be to understand. It only increases the chance, but it need not have to find the ideal assignment. We then compare the number of iterations that are required post initialization, and that also in this particular example for k-means plus plus, it happens to be with an average of around 4.2 iterations as compared to the random one with around 9 iterations to convergence. Thirdly, we look at the time taken by each of these. This is the time taken is also including the initialization. So random initialization will take almost no time, whereas k-means plus plus, right? So for every data point, you're sort of finding the distance between every cluster that you have chosen, and then you have to normalize it, then you have to pick it up, and you have to do it, right? So it sort of scales with the value of k and also with the size of the data set. So this result especially might not be the case for other data sets. It is very data set dependent, but for this particular example, we see that both sort of roughly take around the same time, even though the modal time is very small for k-means plus plus at around 0.1, 0.25 seconds, but on average both of them take an equal amount of time to converge. Alright, so let's go through some numericals in this particular week. Consider the following one-dimensional data set. K-means algorithm with k is equal to 3 is run for the above cluster assignments where mu1 is minus 15, mu2 is 0, and mu3 is 5. So first we initially start off with our cluster assignment step. We need to find for each data point the distance between them and the closest particular cluster, right? So here, for example, we take the minus 15 as our particular data point. We find the distances from minus 15 to mu1, mu2, and mu3, and we identify those to be 0, 15, and 20 respectively. Therefore, minus 15 is assigned the cluster of mu1, and we repeat this across all of these things. So for here we see minus 15 is assigned the mu1, minus 10 is assigned mu1, 0 is assigned mu2, 5 is assigned mu3, because you can see the color shadings that correspond to the minimum distance that has been observed for each of these centroids. So we do that assignment, we shade the points respectively. So this is the assignment step done, and now we can move on to recomputing our clusters. So for mu1 it would be minus 15 minus 10 by 2, mu2 would remain the same because there is only one data point in the cluster, and mu3 would be adjusted to that particular value. We again do our cluster assignment step. So here you can see the point equal to 5 would actually be updated to mu2, whereas the others would stay roughly the same. And after the assignment we do our recomputation again to the following, and now we've converged. If you calculate the closest centroids for each of these, you see that the assignments don't change, hence k-means has converged for this particular, Lloyds has converged for this particular problem. Do not change, therefore they have converged. The second problem is k-means plus plus problem. So consider the following data set, and k-means plus plus algorithm with k is equal to 2 is run on this data set to initialize our cluster centers. What is the probability that x2 and x1 are chosen by k-means plus plus in that particular order? Since k-means plus plus is a probabilistic algorithm, any assignment is possible, but the probability that is included is what is being tested in this particular question. So initially, the way in k-means plus plus, you initially draw out your data points from randomly, right? So all points are equally likely, therefore it's a uniform distribution. It's 0.2 because you have five data points there. So the probability that x2 is chosen, we want to choose x2, is 0.2. Therefore, so we have x2 in our particular collection of cluster centers that are chosen, and 0.2 we've sort of battled with a 0.2 chance to choose this particular x2. So that is part of the product that we'll be evaluating earlier to find the answer. Secondly, we want to find after x2 what is the probability I choose x1. Now since I have chosen x2, I have to update my probability, right? So I need to sort of score and normalize the score to get the probability. the score is proportional to the squared distance between my data points. So you can see, for example, if you take x3, right, x3 is 0, x2 is 2, so the distance between x2 and x3 is 2, and the squared distance is 4. Therefore, that gets the distance d squared x of 4. And if I normalize these, I get the following probabilities. And now I want to choose x1 after x2. Now I see that the probability of choosing x1 after choosing x2 is 0.22. Therefore, I do just that. I battle with a 0.22 probability to choose x1. I have x1 in my collection, and we are done. We because k is equal to 2, and our algorithm is done, and our answer evaluates to 0.044.